Still, we're talking about method of characteristic. Right? So again, for the method of characteristic, what you're dealing with is a linear homogeneous second-order differential equation with constant coefficients. From here, you turn it into a characteristic equations, therefore the name method of characteristic. So in the last two lectures, we tackled the case of two distinct roots, the case of repeated root. Now we go into for the last case of the complex roots. And in this lecture, we're going to form a characteristic polynomial and identify complex roots. And we're going to present the complex root in the form of lambda plus and minus I times mu. And I'm going to explain lambda and mu later. And then you find the general solutions of the form here. I'm going to guide you through the process of going from the complex root down to this equation or this functions where you don't see the complex information anymore. Alright, so as I mentioned, this is still the case of linear homogeneous second-order differential equation with constant coefficients. This is the form that we are working with. So from this differential equation, we turn it to the characteristic equation of the form AR squared plus BR plus C equal to 0. You can factor this equation, or you can use the quadratic formula to find the root of the characteristic equations. And here, in the case of, in this lecture, we assume that b squared minus 4ac is less than 0. That is, this term under the square root is less than 0. And therefore, you're going to get a complex root of the form. So we're going to get two solutions, right? In the case of complex root, so R1 equal to lambda plus I mu, and R2 equal to lambda minus I mu. So for lambda is called the real part and mu is called the imaginary part. Later we're gonna have some physical interpretations of lambda and mu, but that's for later. And very similar to the case of two distinct roots, for the case of complex roots like this, you can base on R1 and R2 to write out the solutions of the differential equations. So the corresponding solutions to the original differential equations are, you have y1 equal to e to the r1 t, or e to the lambda plus I times mu t, and y2 is equal to e to the r2t, or this is e to the lambda minus I mu times t. Okay. Still, in this type of solution, you see imaginary numbers. Right? For I, in this case, the imaginary number. But practically, when you do this type of problem, when you get to the general solution of the differential equation for the case of complex roots, the solutions tend to have this form, and we're going to use this type of, or this form of solutions to work with the differential equations. Okay, so the general solution is going to look like this. So y equal to c1 times e to the lambda t times cosine of mu t plus c2 times e to the lambda t times sine of mu t. Okay, and you may wonder why this general solution is coming from, provided that we have complex root in this, right? In the case of characteristic equations. And also from y1 and y2 here, how could we get the general solutions? So in order to go from this step of e to the lambda plus or minus I mu times t to this general solutions, I'm going to show you the procedure, and in order to go through the procedure, I need to introduce to you the Euler's formula. So this is a very famous formula. That is e to the I theta equal to cosine theta plus I times sine theta, and you can negate it to get e to the negative I theta. Right? So difference between these two is just the plus or minus sign. So I in this case is going to be an imaginary number, and therefore I squared equal to -1. This can be easy to prove this formula using the Taylor expansion, so Maclaurin's of series. That cosine or exponential functions can be written as the infinite sum, and you can take it to combine the the part with the even terms and the part of the odd terms. The part of even term can be written as cosine of theta, and the part of odd terms can be written as sine of theta. And that's how you prove this formula, but I'm not going to spend time and prove it. I'm just going to directly use the formula for my derivations. Okay. Again, I'm going to show you how to go from y1 and y2 to the general solutions of this form. Okay, so we use the Euler's formula to rewrite the solutions. So we use the Euler's formula to rewrite the solutions of y1 equal to e to the lambda plus I times mu t, and y2 equal to e to the lambda minus I mu t. Okay. That is, so I'm going to use this formula right here. So for e to the y1 equal to e to the lambda plus I mu t, I get this is e to the lambda t times e to the I mu t. Okay. Now, e to the lambda t stay the same. I'm going to apply the Euler's formula for this term's e to the I mu t. And I'm going to get cosine of mu t plus I times psi of mu t. Okay, so that's one. Now for the second solution, y2, I get y2 equal to e to the lambda minus I mu t equal to e to the lambda t times e to the negative I mu t. So this is for the Euler's formula of this form. Okay, so e to the negative I theta, for theta in this case mu t. So I get e to the lambda t times cosine of mu t minus I times psi of mu t. Okay, so far so good. Any questions? So in finding the solutions of the second order differential equations, we want to assure that y1 and y2 are linearly independent, or they form a fundamental set of solutions. Okay. So we assume that y1 and y2 are linearly independent. Then the general solutions can be written as a linear combination of y1 and y2. That is, so y is equal to c1 times y1 plus c2 times y2, and y1 and y2 are of this form. Okay. So c1 times e to the lambda t times cosine of mu t plus I times psi of mu t plus c2 times e to the lambda t times cosine of mu t minus I times psi of mu t. Okay. So that's where you get the general solutions. So the next step is to distribute and combine like terms. So I have c1 e to the lambda t times cosine of mu t plus I times c1 e to the lambda t times psi of mu t plus c2 times e to the lambda t times cosine of mu t minus I times c2 e to the lambda t times psi of mu t. So combine like term here, I get c1 plus c2 times e to the lambda t times cosine of mu t plus I times c1 minus c2 times e to the lambda t times psi of mu t. Now we're going to make some assumptions here that, again, c1 and c2 are arbitrary constants. So c1 plus c2 is going to be some arbitrary constant as well, and therefore we're going to get, let's say, capital C1 times e to the lambda t times cosine of mu t. So c1 is the constant, c2 is the constant, so c1 plus c2 is a constant as well. So I just substitute that with a capital C1. Now for the second terms, I have, again, C1 is a constant, C2 is a constant, so C1 minus C2 is a constant. And multiply that with I, even though it's an imaginary number, is still a constant. So I'm going to substitute capital C2 in the place of I times C1 minus C2 times e to the lambda t times psi of mu t. And that's how you get the general solutions of this form. So in general, when we do the problem related to complex root, we write the general solutions of the form C1 times e to the lambda t times cosine of mu t plus C2 times e to the lambda t times psi of mu t. Okay. And you don't have to struggle with capital C1 or capital C2, just use C1 and C2. As now at this point, we know where the formula coming from. Okay. And I'm not going to redo the fundamental set of solutions or linearly independent solutions for the case of complex root because we have already done that in lecture 8. So let me go back to lecture 8 and show you that. Right. So in example 4, which is the last example in the lecture, you have two solutions, y1 and y2, and as you see, they are they are from the complex root of the method of characteristic. Okay, and we show that in this case the Wronskian is different from 0, assuming that mu is different from 0. Okay, and they because of this, the Wronskian is different from 0, leading to the two solutions are linearly independent or they form a fundamental set of solutions. Okay, so that's where you get the general solutions. Now, in practice, you can't just, from the complex root, you identify the value of mu, the value of lambda, and directly write down the solutions of the general solutions without doing the Wronskian. So I'm going to avoid doing the Wronskian here because we already did kind of the general case of the Wronskians. All right. Example 1, want to find the general and particular solutions of the given initial value problem. So you have y prime plus 4y equals 0, and the initial conditions are y of 0 equal to 0 and y prime of 0 is equal to 1. So you want to turn this second order differential equations to a characteristic equations. The characteristic equations is you have r squared plus 4 equal to 0. And from here you have r squared equal to 4r, r negative 4, sorry, or r is equal to plus and minus 2i. Okay. From here you can deduce that lambda is equal to 0 and mu is equal to 2. We can deduce that lambda is equal to 0 and mu is equal to 2. Okay. Then the general solutions of the differential equation is you have y equal to c1 times cosine of 2t plus c2 times psi of 2t. Again, I'm following this particular setup here. If you know the value of lambda, if you know the value of mu, you can just directly use the value of this general solution setup. In this case, lambda is equal to 0, so e to the 0 is equal to 1. Mu is equal to 2 in this case, right? And you don't have to worry about plus and minus in this case because it just give you the idea that there are two solutions or two roots, and therefore that's why you have one is cosine of 2t and the other one is sine of 2t. Again, I'm not going to ask you to do the Wronskian for this type of problem anymore, but in the homework, I might ask something related to it, but not going to be too difficult to do for the Wronskian. So you got the general solutions. Now, given the initial conditions, you can find particular solutions. So
one quick question.
Sure.
So we can assume lambda and mu's values based off of the fact that we know from our previous example what our values of y1 and y2 are. So lambda plus I times mu.
Mm-hmm.
So that's how we get
yes.
Okay.
Yes. So based on, you're right. So based on this setup, that for the root of the complex root of the characteristic equations, that you can identify lambda and mu that way. Right? So from this example, even though you don't see lambdas, but technically what you have is r1 equal to 0 plus 2i, and R2 is equal to 0 minus 2i. And so you can assume that, you can deduce that lambda is equal to 0 and mu is equal to 2. Okay. Good.
Yep.
Any other questions? Right, so given the initial conditions, y of 0 equal to 0 and y prime of 0 equal to 1, we get that. So y of 0 is c1 times cosine of 0 plus c2 times sine of 0. So sine of 0 is equal to 0, and cosine of 0 is equal to 1. Therefore, you get c1 equal to 0. Now, you're going to find c2. So y prime of t is equal to negative 2c1 times sine of 2t plus 2c2 times cosine of 2t. Therefore, y prime of 0 is going to be negative c1 times sine of 0 plus c2 times c2 times cosine of 0. This term is 0. And you get 2c2 equal to 1, or c2 is equal to 1/2. Then the particular solutions is y of t equal to 1/2 times sine of 2t. Okay, so that's the procedure to get the general solutions and particular solutions. Again, I want to emphasize that for the case of complex root, you just need to write down general solutions without calculating the Wronskian. Right? So in the last homework assignment, I do ask you to do Wronskians as a practice to show you where the idea of general solutions coming from. Because when you start with two solutions, you have to make sure that two solutions are linearly independent. And to check if they are linearly independent, you need to check the Wronskian. And also, when you get to the next two methods, the method of undetermined coefficients and variations of parameter, you still need the knowledge of the Wronskian. You cannot get away with it. So I just want to minimize the work for the homework, but the idea should be there. Right? That for the complex root, even though you get two solutions, you still need to get to calculate the Wronskian. The Wronskian have to be different from 0, and because of that, you're allowed to write down the general solution as linear combinations of y1 and y2. However, when you get to undetermined coefficients in the next lecture and the variations of parameter in the following lecture, you cannot get away with the Wronskian. So therefore, yes, we don't have to do for the complex root case, but in general, you have to. Okay. Now for example 2, I want to find the general and particular solutions of the differential equations y double prime plus 4y prime plus 7y equal to 0. And we have the initial conditions of y of 0 equal to negative 4 and y prime of 0 equal to negative 1. So again, the characteristic equations. Is that of r squared plus 4r plus 7 equal to 0. So if you know how to factor it, you can factor it, but it's not very clear for you to do the factoring. Therefore, you can use the quadratic formula to find the root of these equations. Then r is equal to negative b plus minus square root of b squared minus 4ac divided by 2a. So for b is equal to 4, so negative 4 plus and minus square root of 4 squared minus 4 times 7, and times 1 times 7, over 2. And so you have negative 4 plus and minus square root of negative 4. Did I get 4? So, sorry. It's not negative 4. So what do I have here? 16 minus 28 is 12. Negative 12 divided by 2. So negative 12, that is 12i squared. Divided by 2. 12 is 4 times 3. Take out a 4i squared. You're going to get negative 4 plus minus 2i times square root of 3 divided by 2. You get negative 2 plus and minus I times square root of 3. Okay. And from here, so that's the complex roots. Any questions on this? Okay. Then from here, you can deduce that lambda is equal to negative 2 and mu is equal to square root of 3. Then the general solutions of the differential equation is you have y equal to c1 times e to the negative 2t times cosine of square root of 3 times t plus c2 times e to the negative 2t times sine of square root of 3 times t. Okay. Now that's the general solutions. We're going to utilize the initial conditions to find particular solutions. So given y of 0 equal to negative 4 and y prime of 0 is equal to negative 1. So this is the initial conditions we get. So y of 0 is equal to c1 times cosine of 0 plus c2 times sine of 0. Let me be careful here. So c1 times e to the 0 times cosine of 0 plus c2 times e to the 0 times sine of 0. This term is equal to 0 since sine of 0 is 0. So cosine of 0 is equal to 1, e to the 0 is equal to 1. So you can get that c1 is equal to negative 4. And to get c2, we can use the second initial conditions. Y prime of t is negative 2 c1 times e to the negative 2t times cosine of square root of 3t minus c1 times e to the negative 2t times negative square root of 3 times sine of square root of 3t. So again, this two terms is coming from the derivative of c1 times e to the negative 2t times cosine of square root of 3t. Now the next two terms coming from the derivative of this product. So minus 2 times c2 times e to the negative 2t times sine of square root of 3t plus c2 times e to the negative 2t times square root of 3 times cosine of square root of 3t. So y prime of 0 is negative 2 times c1 times e to the 0 times cosine of 0 minus c1 times e to the 0 times negative square root of 3 times sine of 0 minus 2 times c2 times e to the 0 times sine of 0 plus c2 times e to the 0 times square root of 3 times cosine of 0. Again, sine of 0 is equal to 0, so this term is 0. This term is also equal to 0. And you're left with negative 2c1 plus square root of 3 times c2, and this is equal to negative 1. Right? But c1 is equal to negative 4 already, so you get negative 2 times negative 4 plus square root of 3 c2 equal to negative 1, or square root of 3 times c2 equal to negative 9, and c2 is equal to negative 9 over square root of 3. Radicalize this, and you get negative 3 times square root of 3. And from here, the particular solution is so the particular solutions. So y of t is equal to, so c1 is equal to negative 4. So negative 4 times e to the negative 2t times cosine of square root of 3t minus 3 times square root of 3 times e to the negative 2t times sine of square root of 3 times t. Any questions? Oh, so let me do one more example here to ensure that everything is we are on the same place. Okay, so similar idea, very similar procedure. Given the second order differential equations, start writing down the characteristic equations. From there, you can identify, you can deduce lambda and mu, and you can get the general solutions and use the initial conditions to find the particular solutions. So here, the characteristic equation is you have 16r squared minus 8r plus 145 equal to 0. And you use a quadratic formula to find the root. Okay, so r equal to a plus minus square root of a squared minus 4 times 16 times 145 altogether divided by 2 times 16. And you're going to get a plus minus square root of, so if you do the calculations correctly, you should get negative 9,216 altogether divided by 32. Or this is going to give you a plus and minus 96i divided by 32, or you get 1/4 plus and minus 3i. And from here, you can deduce the value of lambda and the value of mu. Then lambda is, or we can deduce that lambda equal to 1/4 and mu is equal to 3. Then the general solutions is so general solution is of the form y equal to c1 times e to the 1/4 t times cosine of 3t plus c2 times e to the 1/4 t times sine of 3t. And then we can, that's the general solutions. We're going to use the initial conditions to find C1 and C2, and therefore the particular solutions. So given y of 0 equal to -2 and y prime of 0 is equal to 1. We get that y of 0 equal to C1 times e to the 0 times cosine of 0 plus C2 times e to the 0 times sine of 0. Again, this term is 0. You're left with just C1, and that is equal to -2. Now to get C2, you use the second initial conditions. So y prime is equal to C1 times 1/4 e to the 1/4 t times cosine of 3t minus C1 times e to the 1/4 t times -3 times sine of 3t. So again, there's two terms coming from the derivative of this product. And the next two terms you're going to get is from the derivative of this product. So you have plus C2 times 1/4 times e to the 1/4 t times sine of 3t plus C2 times e to the 1/4 t times 3 times cosine of 3t. Well, y prime of 0 is equal to C1 times 1/4 times e to the 0 times cosine of 0 minus C1 times e to the 0 times -3 times sine of 0 plus C2 times 1/4 times e to the 0 times sine of 0 plus C2 times e to the 0 times 3 times cosine of 0. So this term is 0. This term is 0 as well. And you're left with 1/4 times C1 plus 3C2, and that is equal to +1. But C1 is equal to -2. You got 1/4 times -2 plus 3 times C2 equal to 1. Or you have 3C2, this is -1/2 plus 3C2 equal to 1, or 3C2 is equal to 3/2, or C2 is equal to 1/2. And because of this, you have the particular solutions of the form y equal to C1 in this case again is -2, so -2 times e to the 1/4t times cosine of 3t plus 1/2 e to the 1/4t times sine of 3t. So that's it for the case of complex root. And in this case, we talk about the complex root of characteristic equations. From here, you can identify the real part and the imaginary part and write down the general solutions of the differential equations, then utilize the initial conditions to find the particular solutions. Also, we derive the general solutions using the Euler's formula. So given the complex root, you can write the corresponding solutions to original differential equations, and from there you utilize Euler's formula to arrive as the general solutions.